Namaskar friends. Today I'll be continuing my lecture series of General Organic Chemistry in which I'll be taking lecture 12. First of all, I would just like to apologize that I couldn't give the lecture for last 10 days. I was unable to deliver the lecture because I was not feeling well, due to which I couldn't give the lecture. Okay, apart from that, now today we will continue our part of reaction intermediates we had done, which we had done in lecture 11. If you remember, in lecture 11th, I had taken reaction intermediate where different types of reaction intermediates like carbocation, carbanion. Okay? In that carbocation is tertiary is more than secondary is more than primary carbocation. And then we had done with carb anions, right? In carbanions, we had done the stability order of carbanions, not only that, and then what are the different parameters by which carbanion is stabilized. Remember, in the first case, we have taken electronegativity, then inductivity to be more precise. So 2 points we had already done. Today I will start with the third point. Why? What's the reason for more stability of the carbanion? Right? Okay. So today we'll do the third one. Third one happens to be, you can say, delocalization or resonance. Delocalization means delocalization of electrons. Means the electrons is not concentrated on a particular carbon or not particular atom, but it is delocalized completely. That is the same way it's known as resonance. Now, if we take two different examples, first one happens to be, take for example, allyl, then benzene. Now, what do you mean by allyl? See, both allyl and benzene are stabilized by resonance. Are stabilized by resonance. Resonance or delocalization, because resonance is nothing else but delocalization of electrons. Right? Now this take for allyl CH2 double bond CH, then single bond CH2 minus. Right? CH. This happens to be more. This happens. It's lesser stable than phenyl. Yeah, you can say benzyl carbon. This is lesser than phenyl, I will say twice, CH minus. This is lesser than phenyl thrice C. Right? That means I can say a tertiary phenyl is more stable than secondary, which is more stable than primary, and which is more stable than allylic. Right? If we do the resonating structures, then this will give 2 structures. This he will give me 4 structures. Then this will give me 7 structures, and this will give 10 structures. Just try to do the resonance, you will come to know. So 2, 4. The more the resonating structure, more will be the stability, as we know. Okay, this was the third one. Now the fourth one. Stabilization due to presence of carbonyl group, or you can say NO2 group, or you can say CN group. That means only unsaturated groups. Primarily. And this stabilization is due to the resonance, specifically due to the presence of these unsaturated groups. Take for example, we'll take one example, CH2 dash C double bond O dash R. Take for example, this is the now. Take for example, this will go here, right, and then this will go. So this will be CH2 double bond C O minus, and this will be R, right? This is known as enolate ion. right? CS2 C double bond O R. In this it will go here, and then this will become here. This is known as enolate. Similarly, I will do it CH2 dash N double bond O single bond O minus. This is plus. Right? Now, suppose if I same thing if I do here, and then this I'll do here. So this will be CH2 double bond and single bond O minus single bond O minus. Okay. So if I take this is structure 1, sorry, this is structure 2 and this is structure 1. Similarly, this will be structure 1, another, and this will be structure 2. So we can say the structures 2 is more stable than structure 1. Structure 2 is more stable than structure 1. Why structure 2 is more stable? Because the negatively charged is present on the electronegative element, right? Now I think so. From my previous lectures, you have understood why what do you mean by these short forms? Negatively is written by minus. Okay, charge by presence of electronegative element. So since in this case, in this structure, though negative charge is present on electronegative element O, here also it is present on electronegative element O. So the presence of negatively charged on the electronegative element imparts more stability to that particular ion, right? Now, another point. Then we saw 2, 3, 4, and now it is 5th. Stability of aromatic compound. Stability of aromatic compound. See, the stability of aromatic compound means the delocalization of the charge on the aromatic ring. Nothing else but the charge on the aromatic ring. Okay? Now, what do you mean by aromatic carbon ion? First of all, suppose this and this is minus. Okay. Fine. So I will write the resonating structure. This will go here, then this will go here. And this will go here, and this will go here. Sorry, extremely sorry. Right? Yeah. So now we can see it is the negatively charged species is getting delocalized. Now we know as per the Huckel's rule. Huckel's rule, it has to satisfy 4n plus 2 pi electrons. See, for a aromatic for a compound to be aromatic, for a ring to be aromatic, it should satisfy the Huckel's rule, which is 4n plus 2 pi electrons. Yeah. Now, where n can be 0, 1, 2, 3 for anything, where n can be 0, 1, 2, 3, whatever. Suppose if I put for n as 1, 0, 1, 4 as sorry. So first of all, how many pi electrons are there? 2, 4 and 6, which is 6 pi electrons. Okay? Now this 6 pi electrons should fit in this formula. So 4, if I take 4 into 1 plus 2 will give me, that is 6 pi electrons, right? Because if I take n is equal to 1, okay, then it is coming as 6 pi, not this 6 pi. So it is satisfying this particular Huckel's formula, and it is a planar structure. Planar structure form. It is a planar structure then satisfying the Huckel's formula. So this compound becomes aromatic in nature, right? So by this way we can find out the aromaticity of any ring. If you want to find whether a specific ring is aromatic or not, then we can do it by this function. Take for example now again any ring, for that matter any ring. I think so you might have understood. Any ring we can take where it is negatively charged. Say right, fine. No. We will see the stability pattern of different carbanions. Fine. I will say aromatic carbanion is more stable than benzyl, which is more stable than allyl. This is very important. CH triple bond CH minus. Then this is more stable than alkyl. And within alkyl we can say CH3 minus is more than primary, which is more than secondary, and which is more than tertiary. Fine. So make it a note of it. Aromatic carbanion is more than stable than benzene, which is more than allyl, which is more than alkyne, and which is more than alkyl. In alkyl groups, this is the pattern for carbanion, right? That means primary is more stable than secondary, is more stable than tertiary in terms of alkyl carbanion. Now, first we saw carbocation, then we saw carbanion, and now the third type of reactive intermediate is carbon-free radical. Carbon-free radical. Basically, what do you mean by carbon-free radical? Carbon-free radical is nothing else but homolytic fission of a covalent bond. Homolytic fission of a covalent bond gives formation of a radical. I'll just by example I'll show you. Take for example this. Suppose this is H, this is H, this is H, this is H. This is the bond. Now suppose there is a homolytic fission. That means homolytic fission means what? There is an equal division of electrons. This is the electron of hydrogen and this is the electron of oxygen. When this bond breaks, then one electron will go to this and the another electron. Similarly, one electron will go with the carbon. So this happens to be and this is another fine. This electron stays with it. So it has how many? 2, 4, 6 and 7. Therefore it has 7 electrons in its outermost shell, or 7 electrons in its outermost orbit. If it has 7 electrons, that means it is unpaired, that means it is paramagnetic. This shows magnetic properties, and they are highly reactive in nature. highly reactive. I think so you might have understood this free radical. What is this free radical? Equal division of electrons. One electron goes to hydrogen, the other one single electron goes to carbon. So now, so this carbon atom has got its own electrons. So it has 2, 4, 6 and 1 7. So it has 7 electrons in the outermost shell, most orbit, right? Therefore it is paramagnetic in nature. It's highly reactive. Now we will see stability pattern of alkyl radicals. Of alkyl free radicals. Alkyl free radicals. Now this, there, as we saw, there is one single electron. That means it requires electrons. It requires electrons to get a complete octet, right? That means it requires. Therefore, it will require such type of groups who are electron donating. So tertiary radical is more than secondary, which is more than primary, and which is more than CH3 dot. Right? Because tertiary carbon atom will be bonded with 3 different carbon atoms, methyl groups, and that will be donating electron towards the carbon free radical, leading to the stability of leading to its stability, right? Then tertiary is more than secondary, is more than primary. So you can say, what is the reason behind that? The reason behind that is hyperconjugation, we can say. Then inductive effect, we can say. That means, to be more precise, plus I effect. Plus I effect. Plus I inductive effect. Fine. So this shows the stability of the alkyl radical. Now, we will see some free radical. What do you mean by free radical reaction? Free radical reaction. Free radical reaction. They take place in the presence of, these free radical reaction take place in the presence of peroxides, heat. In the presence, this peroxide or heat or UV or electricity. These are the 4 conditions, you can say, to be more precise, who are responsible for free radical reaction. These things are. Yeah. So there are 3 steps in free radical reaction. First step, we'll go step by step. First one is initiation. Initiation. B is propagation. Propagation. And C is termination. And termination. So first we'll go with initiation. As the name itself indicates, it leads to first the initiate of electrons. Suppose we take any reaction. So now first thing, take for example chlorine, Cl2 chlorine gas. So this is homolysis, so this will break and this will break. So it is shown by a single-headed arrow, because one arrow, only one electron is going, not a double-headed arrow, only a single-headed arrow. So this will form Cl dot plus Cl and dot, and this is a continuous process now. This is a continuous, every time chlorine is going to break into Cl dot Cl dot. Okay, this is a continuous process. Now, what will be step 2? Step 2 will be propagation. Right? Propagation. Now, what take for example, this is CH3 and this is CH4, methane. In this again there is a breakage, and this, no doubt, propagation is an exothermic step. Exothermic step, that means heat is evolved, heat is released. So again this single-headed arrow, fine. Now what will happen? This propagation, this will react with one of the chlorine free radical, so this will also react, then it will form CH3 dot plus HCl, right? And this will be again a continuous process. Methane will be continuously breaking, and Cl obviously in the first step is continuously getting formed, and this will be reacting with the CH4. right, to form HCl. Now this will be continuous. No, but this, if I want the reaction to take place, then there should be some termination which should be there. It has to break somewhere, the termination. So termination, the free radical which is generated in step 2. In step 2 is this. The free radical which is generated in step 2 basically happens due to the step 1 also, we can say, because unless and until this chlorine free radical is generated every now and then obviously it is going to attack on the methane. It is going to react with methane, right? If there is no presence of any chlorine radical itself, then obviously the reaction will be terminated. Then there will be no breakage of this, no formation of methyl radical, right? So the culprit is chlorine radical. So far we will have to stop this chlorine radical. For that, to what we have to do, it has to be destroyed by addition of impurities like chloroform or carbon tetrachloride. Take for example, one chlorine dot is formed plus this is. Now due to the presence of impurities, this Cl2 radical, they itself form chlorine gas, and once they form chlorine, these two radicals will get combined to again form chlorine. Again they will be forming, again they will be forming. This will be a reversible step. This initiation itself will be a reversible step, right? That means there will be no presence of any free radical. That's why what will happen, the reaction will get terminated and then it will stop here. So you saw initiation, propagation and termination. Termination, it has to be done only in presence of some impurities like methane or it. As you know, in this class 10th you have done, basically if it's basically free radical is an uncontrollable reaction. As we are writing here, no doubt methyl sorry, just a second, free radical, I forgot one more thing. This, what will happen then, this free radical will react with another chlorine free radical. These two people will react to form methyl chloride. So ultimately methyl chloride. So ultimately there will be formation of methyl chloride plus HCl, right? Methyl chloride and HCl. Now this basically is an uncontrollable reaction. So again what will happen? Suppose methyl chloride is there. Now this again H is there. Again it will break into CH2Cl dot plus again the same thing will happen. Cl dot is there. These two people will again react. So it will form CHCl2 plus HCl. Again it will react with a chlorine radical to give CCl3. CH2Cl2, then this will be CHCl3, then this will form CCl4. Fine. CH2Cl2, which is known as dichloromethane, then this will react with another chlorine radical to form CCl4. That means as long as hydrogen is there, this reaction is uncontrollable. Now here the reaction gets terminated. And we get, this was, if you see, explained in class 10th, right? Okay, so this is the some initial free radical we have seen. Now we have to see the stability of free radical. Right? Stability of free radical. Stability of free radical is nothing else but tertiary will be more stable than because obviously it has one single electron. That means it wants more electron with center to give electron to that carbon atom so that it can become stable. means you can say R. Oh, sorry. Right? Secondary. Similarly, tertiary, secondary, and primary. Fine? No. I will write a whole series now. Once again, I will repeat it. Phenyl 3 radical is more than phenyl twice CH radical, which is more than phenyl CH2 free radical, which is more than, I will say, CH double bond CH R means allyl radical. Allyl radical is more than CH2 double bond CH dot CH2. Right? Now this will be more than tertiary radical, which will be more than secondary, which will be more than primary, and which will be henceforth more than methyl radical. Right? Make a note of this. Now, the stability of alkyl radical is directly proportional to the number of carbon atoms attached. Carbon atom attached, number of carbon atom attached to the alkyl free radical. Alkyl free radical, right? Now, so this happens to be this carbon and carbocation free radical basic concepts I have told you. Now, later on lectures we will see the application of these three reactive intermediates. Fine? No. Now we'll go for, if you remember in lecture 5, in lecture 5th, we had done some basic concepts. What do you mean by a nucleophile? What do you mean by an electrophile? Nucleophile is electron rich, electrophile is electron deficient. A means electron rich, therefore a nucleophile has a liking for an electrophile, that is a positively charged species. In lecture 5 everything I have explained you. If you want to again, you can go back to lecture 5 and see. Okay? Now today we will do in detail about nucleophile and electrophile and its application, mostly its application. Basics of nucleophile and electrophile, refer lecture 5, and now in detail applications of nucleophiles and electrophiles. It's very important, right? Now, what do you mean by a nucleophile? I'll write in a short form, nucleophile Lu minus, which is electron, nothing else but electron donor. That means I can say electron rich. That means it has a liking for positively charged species, charged center. Right? Similarly, I'll say what do you mean by electrophile? Electrophile E plus I will write electron acceptor, electron deficient, liking for negatively charged center. Negatively charged center is nucleophile and positively charged center is electrophile. Fine? Yeah. Now, nucleophiles are of basically two types. Nucleophiles are of basically two types. One is a charged nucleophile. Charged nucleophile. For example, H minus, OH minus, OR minus, then CH3 minus, then X minus, RS minus, thiol, right? Now there are neutral nucleophiles. Neutral nucleophiles. Neutral nucleophiles in which the central atom has a complete octet. Complete octet and at least one lone pair of electron. Lone pair of electron. At least lone pair of electron on it. Lone pair of electron. And the other atom which is attached to the I'll write a short form, central metal atom, CMA. Central metal atom is not, make a point, not electronegative. Not electronegative. That means it should be electropositive. That means it should be electron donating. Central metal atom has a complete octet and it should have at least one lone pair of electron on it. And the other atom attached to the central metal atom is not electronegative. That is, it should be electropositive. Right? Now we'll see, take an example of this case. Take for example ammonia. It's a lone pair of electrons. Then you can say amine, RNH2 primary amine, normal amine, okay? Then NH. Then you can say tertiary amine. Right? Then you can say H2N and NH. Right? Now we can say another H. These are few compounds with a lone pair of electrons. Right? Then alcohols. Right? Then ethers. Right? And then alkenes, alkynes, then benzene. These are all neutral nucleophiles. Fine. Just make a note of it, all these things. Right? Neutral nucleophile. And now another third type of a nucleophile. First we saw charged nucleophile, then we saw neutral nucleophiles, and now the third type of nucleophile, which will be ambident nucleophile. Ambident nucleophile. What do you mean by ambident nucleophile? Ambident nucleophile are those species who have two nucleophilic centers. Two nucleophilic centers. Two nucleophilic center means two electron rich centers. Take for example C triple bond N. This is rich in electron and this is minus. That means this has two nucleophilic centers, right? C triple bond N, then O dash and iso minus charge, right? ONO, nitro and isonitro. This is isonitro. Then O minus dash S, O, then dash OH, and this. Fine. This has lone pair of electron. So it has two electron rich centers. Then similarly we can say CH2 double bond CH dash CH2 minus. This is one of the center, and plus alkene is also one of the nucleophilic center. This is also nucleophilic center. This also can act as, this also can attack on an electrophile, positively charged species. Similarly, benzene is also ambident nucleophile because this CH2 minus also can be attacked. Even the benzene ring, the lone pair of electron which is present on the benzene ring, they are also one of the nucleophilic centers. So these are ambident nucleophiles. Fine. So these are the different types of nucleophiles. Fine. Now Nucleophiles are Lewis bases. Lewis bases. Nucleophiles are Lewis bases. Lewis bases in the sense electron donor. That means electron donor. Lewis bases are electron donor, right? Lewis acid is what? Electron acceptor is known as an acid, electron. But Lewis base is a electron donor. But make it a point that nucleophiles are Lewis base, but not all nucleophile bases are not all Lewis bases are nucleophiles. Nucleophiles are Lewis base, but not all Lewis bases are nucleophiles. Just make it a point in. Yeah. Now we have finished nucleophile. Now we'll go with electrophiles. Electrophiles. Now what do you mean by electrophile? As you know, electrophiles are positively charged species. Positively charged species, right? That means I can say it is their electron acceptors. That means, can I say they are Lewis acids? They are Lewis acids. They have a complete octet. Nucleophile was incomplete octet. So, a nucleophile was a complete octet. This is an incomplete octet. Extremely sorry. This is an incomplete octet. Nucleophile was a complete octet. Nucleophile was a complete octet, but electrophile is an incomplete octet. Right now, example we'll see. H plus. So H plus is an acid, electron acceptor. Electron acceptor is known as an acid. H plus is an acid. X plus also is an acid. X plus means halogens. We take for example chlorine plus is an acid. Then R plus means carbocation. They are electrophile. And O2 plus, they are electrophile. That means I will say this is an acid. Then NO, right? NO. Then SO3H. Can say all cations are charged electrophiles. These are the cations, carbocations. Cations are charged electrophiles, positively charged. Now we will see accordingly there are neutral electrophiles. Neutral electrophile, that means the central metal atom has an incomplete octet. Central metal atom has an incomplete octet. Example, BeCl twice. Then you can say borane, BH3 borane. Then ZnCl2. These are neutral nucleophile compound. ZnCl2. Then you can say AlCl3 is an electrophile. Then FeCl3 is an electrophile. Fine. Now, with the central metal atom has an incomplete octet. Now, just remember, mind it. Incomplete octet is BeCl2, borane, zinc chloride, aluminum chloride, and FeCl3. Right. In neutral nucleophiles, as first case is incomplete octet. The second case happens to be in neutral electrophiles. The first case was an incomplete octet. Now the second case, where the central metal atom has a complete octet. Or you can say complete expanded octet. Take for example SnCl4, or you can say SiCl4. We can say PCl5, SF6, IF7. These are all important reagents which are going to come in our future chemical reactions, and these are taken as a reagents, right? No. No, there are organic compounds which act as electrophile as well as that are both nucleophile and an electrophile. Organic compounds. That means carbon atom of an organic compound bonded with. Suppose if a carbon atom is bonded with oxygen or nitrogen or sulfur by a multiple bond. Therefore, that will behave as a nucleophile, means a carbon atom, sentimental atom bonded with oxygen, nitrogen, sulfur by multiple bonds will act both as a nucleophile as well as an electrophile. Example. Take for example aldehyde. Right? Now since oxygen is an electronegative element, so this will be minus charge and this will be a positive charge. So this becomes a nucleophile and this becomes an electrophile. This is an electrophile and this is a nucleophile. So aldehyde. Similarly will be the case with C double bond O ketone. Similarly will be the case with C double bond O acid. Similarly will be the case with ester. Similarly will be the case with RC double bond O NH2. Similarly will be the case with RCl. Fine. No. Again, it's containing smaller electronegative value like oxygen or chlorine are known as hard nucleophile. Take for example F minus, OH minus, RO minus, SO4 minus. These are hard nucleophiles. Ether RMGX. Right? These are hard nucleophiles. And nucleophiles containing larger atoms, like that means below the, as we go down the group, chlorine, अपना iodine, sulfur, selenium, phosphorus. Fine. Take for example I minus, RS minus, S minus 2, R3, P, can say then alkenes, alkynes, and aromatic ring. They are hard nucleophiles. They are soft nucleophiles. They are soft nucleophile. So, did you come to know what do you mean by hard nucleophile and soft nucleophile? So, hard nucleophile means it is strongly a very, very strong nucleophile. Hard nucleophile in the sense it's a very strong nucleophile. And soft nucleophile means it is a very weak nucleophile. Soft nucleophile is very weak nucleophile. It will not, whenever a nucleophile, this soft nucleophile comes for reaction, it reacts very slowly because it's very soft. That means its reactivity is very slow. But on hard nucleophile, it's a very strong nucleophile. That means hard nucleophile is known as strong nucleophile. That means it will react immediately, very fast. Now, you can say a negatively charged nucleophile a negatively charged nucleophile is stronger than species with no charge. More precise, no negatively charged. Take for example OH minus is a stronger nucleophile than HOH. Right? Similarly, we can say NH2 minus is a stronger nucleophile than OH. Sorry, extremely sorry. Just cancel it from here. Once again, I have OH minus is then HOH. Then I will say SH minus is a stronger nucleophile than HSH. Fine. Now we'll see nucleophilicity. Nucleophilicity increases. Nucleophilicity increases down the order of the purity level. Take for example, I minus is more than bromine, is more than chlorine, is more than fluorine. So the nucleophilic, this is more nucleophilic as compared to bromine, as compared to chlorine, as compared to fluorine. So, and if bulkier groups, and similarly, nucleophilicity decreases is down, decreases, this is increases, and this is decreases it from left to right. Of purity decreases. Take for example, I will say CH3 minus is more than NH2, because if we see carbon comes previous to N. First comes carbon and then comes nitrogen. Similarly, I will say NH2 is more than OH minus because N comes before O. Fine, before O. And similarly, I will say OH minus is more than F. Right? So in periodic table, if you see carbon comes first, then comes nitrogen, then comes again oxygen, and then comes fluorine. Right? If you know in periodic table, it is BCNOF: boron, carbon, nitrogen, oxygen, and fluorine. So like that. Fine. Okay. Yeah. Now, bulkier groups attached to the nucleophile, attached to the nucleophilic center, you will say, decreases the nucleophilicity. The bulkier group attached to a nucleophile. Whenever a nucleophile center is attached to a bulkier group, then its nucleophilicity decreases. Nucleophilicity decreases if more the bulkier group is attached. Take for example, OH minus is more than So more the bulkier groups are attached to the nucleophilic center, decreases the nucleophilicity. Decreases the nucleophilicity. Right? So today we have done basically everything. All the reactive intermediates, more in detail, in-depth view of nucleophile and electrophile, the different types of nucleophile, different types of electrophile. So I think so it's over for the day for this lecture. You just go through these topics because these are topics are very important now, because henceforth now chemical reactions, different types of reactions, different types of organic reactions are going to come into picture, where all these basic concepts will be used, whether let it be inductive effect, hyperconjugation, reactive intermediates, nucleophile, electrophile, isomerism, everything. Finish off today's lecture. I think so you might have understood this today's lecture, and it was very important. It was very important. So again, I will tell you, just pardon me that I couldn't deliver the lecture for last, you can say 7 to 10 days because I was not well. So I'll meet you in the next lecture in which I'll take different types of chemical reaction, right? So I just urge you and request you that you go through all the lectures and forward it to your friends and to your like-minded people, and do subscribe and like my YouTube channel, and also follow me on my Facebook. So I shall meet you in the next lecture. Thank you. Thank you. Thanks a lot. Namaskar.